This is a guide to calculating equilibrium constants, Kc, for equilibria in OCR A's Chemistry A2 level course. So to begin with, I want you to check your knowledge. Can you write expressions for Kc? So that's Kc is equal to something divided by something. Can you remember this from your first year's chemistry when you had to qualitatively describe the Kc expression? So think back to your first year and can you write expressions for Kc for each of the following reactions? Pause the video here and give that a go. Okay, so to write an expression for Kc, you simply have to write the concentration of the products divided by the concentration of the reactants. However, each species needs to be raised to the power of its coefficient. So the coefficient here is a 2, so SO3 will be raised to a 2. SO2 is also got a coefficient of 2, so we'll raise it to the power of a 2, whereas oxygen here only has a 1 in front of it, that's why it's been omitted, so we raise it to the power of 1, so we don't write that. Next up, we've got the Haber process here. Nitrogen plus 3 molecules of hydrogen go to make 2 molecules of ammonia. We can see here that we've got a 2, so therefore we're going to be raising ammonia to the power of 2, and we've got a coefficient of a 3 here, so we're going to raise the hydrogen to a 3. We can see again it's products divided by reactants, and these square brackets here mean the concentration of each species. Let's go over here to the reduction of hydrogen iodide. Again, we've got a 2 here, but neither species here has a coefficient, so the only species raised to a power here is going to be the hydrogen iodide. The others there essentially are raised to the power of 1. And finally, we've got nitrogen monoxide being formed here, a 2 here, whereas a 1 and a 1 here. So it's essentially the same as the previous example in C, raised to the power of 2, and therefore no powers. So in general, what we have done here is we have written products raised to their coefficients divided by reactants raised to their coefficients. Okay, and that will give us Kc. But obviously, we are going to need some data to be able to calculate Kc. So I want you to think, maybe pause the video here quickly, about what exact data we would need, what data would we need in order to calculate a value of Kc like this. So you can see here that we've got an equilibrium, a reversible reaction equation here. This is called the contact process. So this is making sulfur trioxide from sulfur dioxide and oxygen. And if we were to write an expression for Kc, we would see that Kc is equal to the concentration of sulfur trioxide raised to its coefficient divided by the concentrations of sulfur dioxide raised to its coefficient and oxygen. So fundamentally, the data we need here is the concentration of each species. That means moles per decimeter cubed. Okay, moles per decimeter cubed as given by these units here. They are the units of concentration. And what you should think of this as is how many molecules there are per unit volume. So you can see here I've got this box representing a unit of volume, and I can see that there's a certain number of molecules per unit volume. Okay, so to work out the concentration of any species, you simply divide the number of moles, how many things there are in it, by whatever its volume might be, and that will give you a concentration in moles per unit volume. So we need to know the total number of moles of each species, and then we need to know the volume of the container in order to be able to calculate the concentrations. When we can calculate the concentrations, we can calculate Kc. Here's an example. We've got this contact process that we were just looking at with its sulfur dioxide, oxygen and sulfur trioxide, and it was left to reach equilibrium in a 5 decimeter cubed container. Okay, so that we've got a volume there. The equilibrium mixture was found to contain 2 moles of sulfur trioxide, that's that there, 0.5 moles of sulfur dioxide and 0.25 moles of oxygen. Notice how this is the quantities of each reactant at equilibrium, so when it's reached equilibrium. But also notice how we're only given the quantities in moles, and we need them, based on our idea of the equilibrium expression, we need these in moles per decimeter cubed, not just moles. So what we're going to have to do really is, after we've written our Kc expression for this reaction, we're going to have to calculate the concentrations of each. And we have all the information we need here because we know that the concentration is the number of moles divided by the volume. And if we look over at our information here, we've got numbers of moles and we've got a volume. So let's start with SO3 here. We've got 2 moles of it, as we can see here, and we've got a volume of 5 decimeters cubed. So that's just going to be 2 over 5, giving us 0.4 moles per decimeter cubed. Let's move on to SO2 here. How many moles of it have we got? Well, let's have a look over here. 0.5 moles of sulfur dioxide, and the volume's the same. It's going to be the same for all of them because they're in the same container. So that's going to be 0.5 divided by 5, giving us 0.1 moles per decimeter cubed. Let's finish off with the oxygen here. So oxygen, let's have a look here. I can see I've got 0.25 moles of that oxygen and a container volume again of 5. So we're going to divide 0.25 by the 5 and we are going to get 0.05 moles per decimeter cubed. So now, as you can see, I have all of these here. They're the concentrations of each species. So what I can do now is go ahead and just plug those into the equation. But I need to remember to raise them to the power of the coefficient given in the equation. So we're going to input the values and raise to the power. 0.4, that was this one here, raised to the power of 2. 0.1, that was this one here, also raised to the power of 2, square it. And 0.05 here, and it's not raised to any power. So I plug these numbers into the calculator, I do the sum, and I get a number of 320. Well, that's great, but this is chemistry, and we need to remember that we need to give some significance to these figures. So we're going to have to be thinking about units now. Okay, so what we're going to do now is practice calculating indices by applying the law of indices. Now, I want you to think about this in terms of the true reasoning for why the laws of indices exist, because if you understand this, you're going to understand the next part a lot better. But the simple rules are that when you multiply indices, you add them, and when you divide indices, you subtract them. And I'm going to give you an example as to why here. So in this example, we have got a squared times a squared. And this is the same as saying a times a, which is a squared, times a times a. Well, a has been multiplied by a total of 4 times here. You can see I've got 4 a's. Well, that's the sum of 2 and 2. So this is going to be equal to a to the power of 4. So we see here a simple rule that when we multiply indices, we actually add those indexes together. And that's because if we show it the long way there, we're actually multiplying them out. So using the same logic here with our example for b, we have got, let me get my pen, b times b, which is equivalent to b squared, times b. Well, that's a total of 3 times on b, so we're getting b cubed. Okay. Now let's have a look over here at c squared times c to the minus 5. Okay, so applying the same rules, c squared times c to the minus 5 is the same as saying c times c. Now when you multiply something by a negative indice, you're essentially dividing it. So that's times c times c times c times c times c. Apologies for the handwriting. Now, when we divide a like unit, they cancel out. So now what we're left with is 1 over c times c times c, which is equal to c to the minus 3. Now there's a quicker way of getting there, which is essentially 2 plus minus 5 is equal to minus 3. Now, we've got a different unit. It's no longer a single letter, but it's still just as simple. So you could treat mole just like an A. Mole, and we can imagine this here being raised, raised to the power of a 1. That's 1 plus minus 1. Now we know 1 plus minus 1 is equal to 0, and anything raised to the power of 0 is just equal to 1. Okay, so essentially here the units have cancelled out, so there are no units at the end of this. So we just get a 1. Okay, let's have a look now at divisions. So we can see here that we've got a to the power of 5 divided by a to the power of 3. Now in this case, because we've got a division of indices, it's essentially top minus bottom. So 5 minus 3 is equal to 2. So we've got a squared there. Same applies here. 3 minus 6 is b cubed to the power of minus 3, sorry. And finally 6 minus 9, we can see here both are negative. So when we take away, and we're taking away a negative number, we've got 6 minus 9. which is the same as saying 6 plus 9, because we've got two negatives there. So minus 6 plus 9 is equal to 3. And then finally, we've got dm to the minus 9 over dm cubed. So this is minus 9 minus 3. So we've got a minus number, take away a positive number, which gives us minus 12 overall. So the general rules that we should see here are that when you multiply indices, we add them together. And when we divide the indices, we get the top minus the bottom. Now, I haven't gone fully into explaining why this is here, but if you're in one of my classes, we'll go into more detail on that. If you're weak at this, you should practice working with indices, and you need to do that today and now. You need to pause the video, you need to work with indices, otherwise this is not going to make much sense going forward. So now what we're going to do is we're going to use what we've learned about indexes and apply it to work out the units of Kc. These square brackets mean concentration of. Therefore, the units within these square brackets will always be the units of concentration, moles per decimeter cubed. However, each one of these moles per decimeter cubed is going to be raised to the power of the coefficient given in the equation. Therefore, we need to be able to multiply out our units by the power of that coefficient. Now, I'm going to just teach you one more thing about indexes. If you raise an index to the power of another index, so if I had a squared raised to the power, I don't know, of 4, what we would actually do is we would then, rather than adding these, because we're raising that to the power of that, we would multiply out. So that would be equal to a to the power of 8. Okay, so that's important looking at this next part here. I'm going to rub that out so we've got a bit more space. So, first thing I'm going to do is input the units of concentration into each one of these square brackets. And then we can see that we've got to raise these units to the relative powers that are given there. So to do this, we've got to multiply out. So this is essentially here a mole to the 1, and that's times 2, so we get mole squared. This here is a dm to the minus 3. Minus 3 times 2 is minus 6. So on the top, we'll get moles squared dm to the minus 6. Here, we're going to get moles squared dm to the minus 6 again, because it's exactly the same. And here we're multiplying by 1, so it stays the same. So take a second now, and you can see that after these multiplications, we're left with this. Take a second to compare this here with what I have done here. Now what we can see is we need to tidy up this bottom row. So we've got to do mole squared times mole, and dm to the minus 6 times dm to the minus 3. Now here, we're not raising to the power, we're simply multiplying indices. So what we're going to get here is mole squared times that, so we're going to get mole to the power of 3. That's mole squared times moles 1, so moles to the minus 3. We're adding them now. dm to the minus 6 times dm to the minus 3. Minus 6 plus minus 3 is dm minus 9. So we can see now we've condensed this as moles squared dm to the minus 6, top row, over moles cubed dm to the minus 9. So, key points. In the first step, we raised the units of concentration to the power. In the second step, we multiplied out our different units, and now we've condensed them into one final equation. So we're going to finish this now by applying the law of indices. Okay, so moles squared over moles cubed, that's 2 minus 3. 2 minus 3 is equal to minus 1, so we're going to get moles to the minus 1. And dm to the power of minus 6 minus minus 9 is the same as adding 9, so we're going to get dm cubed. Now there's one final thing that we need to do here to tidy this up. There is a standard way of writing indexes, which is that the most positive always come first. We can see that this is a positive number, this is a negative number, so we're going to put this value first. It's the convention to write that first. So we've got dm cubed mole to the minus 1. That's our final units in this case. Now you're probably thinking, if you're quite good at maths and you've looked at the laws of indices before, what a god-awful and long-winded way to go about it. And I agree, this is a long method, but it does encourage understanding. So yes, we've got to our units of Kc, but this took far too long. So what I'm going to do now is teach you a shorter method of coming up with a value for Kc. So we can see here that we wrote an expression for Kc, and we saw that it was products raised to their coefficients divided by reactants raised to their coefficients. And in every one of these square brackets, it's always going to be moles per decimeter cubed. So what we can do is just abbreviate this. You're going to have whatever's in this bracket squared divided by the sum of this. So this is raised to a power of 2, and this is raised to a power of 1. 2 plus 1 is equal to 3. So we've essentially got 2 over 3, which is the same because these are raised to the power of minus 1. 2 minus 3 is equal to minus 1. So this is going to be moles per decimeter cubed raised to the power of minus 1. Moles times minus 1 is equal to moles to the minus 1. Minus 3 to the minus 1 is going to be equal to 3. And there we get our units. So we can see there that this is a much faster method of calculating the units of Kc by simplifying the expression here, applying the law of indices, and then using this power and applying it to the units of moles per decimeter cubed. So what I want you to do now is pause the video and practice calculating the units of Kc for the remaining expressions that were shown in the first starter activity. Okay, so let's have a look at this first one here. We're going to start off by writing an expression for Kc. It's product, concentration of products, divided by concentration of reactants, each raised to the power of their coefficients. So we're going to get this, ammonia, squared, divided by this to the power of 1, and hydrogen to the power of 3 cubed. Now we're going to plug in the units. This is the same as saying n to the power of 2 divided by n to the power of 4, because there's a 1 here, there's a 3 here, the 1 plus the 3 is a 4, so we've got 2 over 4, 2 minus 4 is equal to n to the power of minus 2, moles per decimeter cubed to the power of minus 2, well that would be moles minus 2, minus 3 times minus 2 is equal to 6. That gives us moles to the minus 2, dm to the 6, convention to write it most positive first, gives us dm6 moles to the minus 2. Next example, we have got, this is actually a reaction that can occur in a catalytic converter, where nitrogen monoxide goes to form nitrogen and oxygen. Gets rid of that nitrogen monoxide, which can cause acid rain. So we're going to write an expression for Kc, products over reactants, each raised to the power of their stoichiometric coefficients. We have got nitrogen monoxide raised to the power of 2, nitrogen to the 1, and oxygen to the 1. This is the same as saying 2 over 2, as you can see there. That's 2 minus 2, which equals 0. Anything raised to the power of 0 is equal to 1, but that actually destroys the units there. There are no units left over because the units have all cancelled out. This next expression is identical because we can see that the ratio of reactants and products is the same. So we're going to have products raised to the power of their stoichiometric coefficients divided by reactants raised to the power of their stoichiometric coefficients. This simplifies to n to the 2 over n to the 2, which gives n to the 0. And there are no units. Finally, we've got this here, nitrogen dioxide raised to the 2 divided by this nitrogen tetroxide, I suppose you could call it, raised to a 1. So that's 2 over 1. 2 minus 1 is equal to 1. So timesing the units by themselves essentially gives you moles per decimeter cubed. So now I want to tell you about two different types of equilibria. You've got homogeneous equilibria and heterogeneous equilibria. A homogeneous equilibria involves reactions where all of the species are in the same phase or state of matter. So as we can see here, all of the species in this reaction are gases, and because they're all the same, this reaction can be defined as a homogeneous equilibria. Homogeneous just means all the same. Homo means all the same. So we can see here that they're all in the gas state, therefore it's a homogeneous equilibria. A heterogeneous equilibria, therefore, is an equilibrium where the species are in different phases or states. So we can see here that these three are gases, but this one here is a solid. Okay, we've got a solid here in the form of the carbon. Now, if you've got a solid or a liquid in a reaction, its concentration, square brackets there, are essentially constant because the particle density is so extreme that therefore it must remain the same in comparison to species that are aqueous or gaseous. So Therefore, what we would do is when we write an equilibrium expression, we're actually going to exclude any species that are solids or liquids. We don't put them in the equilibrium expression for Kc. So as you can see here, I'm going to write an equilibrium expression, and I've done products over reactants. There's CO, H2, divided by reactants, H2O. Oh, but look, we can see here that the carbon has been omitted because it's a solid. Okay, and if I had any liquids in there as well, I would also omit those from the equilibrium expression because its concentration is essentially constant. Now, you would only omit these from the equilibrium expression in cases where you've got a heterogeneous equilibria. So let's say, for example, you've got a homogeneous equilibria where everything is a liquid, then we would include them in the Kc expression because they are comparative with one another. However, when it's a heterogeneous equilibria where we've got species in different states, then we omit solids and liquids from the equilibrium expression because in comparison to the aqueous and gaseous species, there is an order of magnitude in which they appear to be constant. Okay, so you would only omit solids and liquids from the equilibrium expression in cases where you have heterogeneous equilibria. So I'm going to show you now how we would calculate Kc when you've got to be able to also calculate equilibrium quantities. So in the first example I gave you, I showed you an example where the equilibrium quantities were already given to us and we had to calculate their concentrations. Now in this case, we are not given the equilibrium quantities of neither reactants nor products. So sulfur dioxide, SO2, that's that there, reacts with oxygen, that's that there, in a reversible reaction, as denoted by the reversible reaction arrow. We can see we've got 2.4 moles of sulfur dioxide and 1.8 moles of oxygen, and they were mixed together in a container of volume 2 decimeters cubed. Now, the key point here is these are not equilibrium quantities. If these were equilibrium quantities, it would have a sentence right here that says, at equilibria, it was found to contain this much of that and that much of that. Okay, it doesn't say this. It says they were mixed together. So this is what we started with. This is what we initially had of the sulfur dioxide and the oxygen. Okay, so this is not equilibrium quantities. We cannot plug these straight into the value for Kc. Now it goes on to say when equilibrium was reached, 1.6 moles of sulfur trioxide was formed. Calculate Kc. So we can see here we've got one value at equilibrium. So we've only got one of the 3 points we need to calculate Kc.
Pump it up, baby! Daytona beat, pump it up, baby! Work that body, work that body! Oh yeah! Take, he's on a lyrical...
Okay, apologies about that. That was to emphasize the point that in cases where you are given only one equilibrium quantity, you need to use something called an I.C.E. table. And the first thing you're going to do to create an I.C.E. table is just write the equation out in the middle of the page and write it quite nice and spaced out so you can write columns beneath it. And what is the significance of I.C.E.? Well, I.C.E. stands for initial, I, change, C, equilibrium, E. Initial, change, and equilibrium. So this is about the initial quantities, the changes in those quantities, and then the quantities that you have at equilibrium. And what I'm going to do is just make that nice and neat. I'm going to create a little table there that we can work from. So you can see there we've made a table. We've made an I.C.E. table. And now what we've got to do is start putting in values into this I.C.E. table. So let's start off. Do we know any equilibrium quantities? Well, yes, we know one. We know the quantity of our product, SO3, at equilibrium, because you can see here it says when equilibrium was reached, we had that much sulfur trioxide. So what I'm going to do is put that value for 1.6 there in here. Okay, I'm going to plop that there. There it is, 1.6. So I know that I have 1.6 moles of sulfur trioxide at equilibrium, but I don't know how many moles of sulfur dioxide I have or how many moles of oxygen I have. So at the moment I cannot calculate Kc. But I do know how much sulfur dioxide I had initially and how much oxygen I had initially, how much went in. So I can put those two values in the first two columns of this table here. So I know I had 2.4 moles of sulfur dioxide to start with and 1.8 moles of oxygen to start with. Okay, now there's one more thing I know as well. And when you think of this is a classic expression that's given all over the internet. I didn't make this one up myself, but if you were making a cake and you started with eggs and flour, let's say you started off with 2.4 eggs and 1.8 flours, whatever that might be. Well, they're your reactants. That's what you start with. This is your product. How much cake do you start with at the start of the cake baking process? You start with none, okay? You've never got any, okay? So we can safely say that at the start of any equilibrium reaction, any reversible reaction, when you put your reactants into the reaction mixture, you have got no product. So in an ICE table, typically, you will have 0 product unless stated otherwise in the question. So we can see here that we've got no product, and we've started off with 2.4 of the sulfur dioxide and 1.8 of the oxygen. Now we can see over the course of this reaction that we've gone from having no product to 1.6 of the product. So that means our product has changed. That's what the C column in the middle here is for. It's changed by plus 1.6. Now we would always expect, based on simple maths, that reactants turn into products. So products are always going to increase. So I'm going to put a plus 1.6 here because that's what our products are increasing by. That's what they're changing by. They're increasing over the course of the reaction. Now this 1.6 value here is proportional to the stoichiometry of the equation. So we can see that it's proportional to a 2 here. So if 2 moles of SO3 is equivalent to an increase of 1.6, then that means that my SO2, which is also 2 to 2 here, so there's a direct proportion between SO2 and SO3, we know that if this was to increase by 1.6, this would proportionally decrease by 1.6 over the course of the reaction. So I'm going to put a minus 1.6 there. Now the reason these are both 1.6 is because they both have the same coefficient. Now the oxygen here is half of the SO3 or the SO2, okay? And it's also a reactant, so it's going to decrease. So half of that is equal to 0.8. So this is going to decrease by 0.8. So notice how these values here are stoichiometrically proportional to the coefficients given in the equation. Now, if I was to say that my sulfur dioxide decreased by 1.6, at the equilibrium, therefore, I've got 2.4 minus 1.6. I'm going to have 0.8 left over. And my oxygen has decreased by 0.8. So 1.80 minus 0.80, I'm going to be left with 1. So now what we can see is that we've used the change in the quantity of product to work out how much the reactants should have changed by, and therefore we've got the equilibrium quantities there of both our reactants and our products. However, remember that these are given in moles, and to work out Kc we need to be working in concentrations, and to work out concentrations from moles we need a volume. And do I have a volume? There's one right there. So now what I can do is go ahead to calculate concentration. So I've got my equilibrium moles of reactants and products that I've calculated using an ICE table. And now I need to convert those moles to concentrations to calculate Kc. I know that concentration is equal to number of moles divided by the volume, and I've got my volume right here. So SO3, let's start with the product. That was 1.6. 1.6 divided by 2, which was our volume, is equal to 0.8. Next up, SO2, which was one of our reactants. That was this one here. We have got 0.8 divided by 2, which gives us 0.4 moles per decimeter cubed. Finally, we're going to go with the oxygen, which we had 1 of, and we're going to have 1 divided by the 2, which gives us 0.5 moles per decimeter cubed. So now we've converted our moles to concentrations. What we can do is slot those into the expression for Kc, which was products over reactants. Let me just show you how we got there. So that was going to be SO3 concentration of squared divided by SO2 concentration of squared times by O2 raised to the power of 1. That's how we were going to get Kc. So we needed those concentrations. There they are. And we're going to just plug those concentration values into there. And we're going to get an 8. Okay, great. 8. Fantastic. But what are the units? Well, let's go back again. Look at the units. So we had a 2 over a 3, essentially. 2 minus 3 is equal to the minus 1. That's moles per decimeter cubed raised to the power of minus 1, which gives you decimeters cubed moles to the minus 1. So we can see here that now finally we've used an I.C.E. table to calculate both the number of moles of reactants and products at equilibrium. We've then converted those to concentrations. We've then applied the Kc expression with those values, and we've worked out the value of Kc and Kc's units. Okay, so let's recap where we've got to today. So the magnitude of Kc indicates the position of an equilibrium. So if you've got a high value of Kc, then that means your equilibrium lies more towards the product. That's desirable if you are a manufacturer of whatever that product might be. You want your equilibrium to lie towards the product. So that's going to give you a large number, because when we do product divided by reactants, if you've got a larger number on top, larger amount of products, then you're going to get a higher value of Kc. If you've got a value of Kc less than 1, then it means your overall quantities of reactants are greater than your products, therefore your equilibrium is going to lie towards the left, lie towards the reactants. Now we've got two types of equilibria, as you remember. We've got homogeneous equilibria, which is the most common example, where all the species are in the same state of matter, same phase, okay? Whereas we could also get a heterogeneous equilibria, which will contain species in different phases and states. Okay. Now to calculate Kc, you need to use the concentrations, and remember that quite often you are given moles, you are not given concentrations, so you need to divide by the volume in order to input those values into an expression for Kc. However, if you've got a heterogeneous equilibrium, you need to make sure that in your expression for Kc you omit liquids and solids, because their concentrations are essentially constant, so they're not needing to be included. However, if it's a homogeneous equilibria, then you should still include the concentrations of those, because then they can compare nicely and they don't screw up the equation. Finally, to calculate an equilibrium quantity, calculate a quantity at equilibrium, you need to use an I.C.E. table, initial change in equilibrium. Go back a couple of minutes if you want to see how that works. And finally, units are easy to calculate if you apply the laws of indices. So there's going to be on this. And I will warn you that this video is useless unless you now do some practice. So what I've done is I've put some links to some worksheets and some further videos in the description below, so that you can go ahead and practice the content that we've looked at today. Thanks very much for your time.